Hi, broadcast.
Right. So we both, in trying to set up the show, have our sort of navigating Google Plus's new structure, and they seem to make events disappear. There's no link for events on the sidebar anymore that I can tell.
And I just can't figure out how to even post from CosmoQuest for some reason.
Oh, maybe it's there. Or am I using the old design of Google Plus and not?
It's all breaking me.
Life has changed. Get used to it, Pamela.
No.
Yeah.
There we go. I found the magic button to click. No, that.
So there was a bit of a malfunction at the junction here. You had proposed bosons as the topic.
Yes.
Susie, or maybe myself, had read it as baryons, and then we'd written the intro for it being baryons, but actually it's bosons. So if you came here expecting to see an episode about baryons, you're going to be sorely disappointed. This is all going to be about bosons.
And to be fair, anyone who had checked the calendar on CosmoQuest had it correct.
Yeah. Anyway, that's not what's going to happen today. It's going to be all about bosons. So if you're watching this and you want to chat with us and ask us your questions, you can go ahead and do so. Just use the Q&A app, and then I will see all your questions. And I'm going to say hi to a bunch of people. Say hi to Nancy Graziano, Stephen Walker, Rick Schwartz, Jim Meeker, and Micah Vogel, Thomas Traniker, Michael Daumer, Tony Lynch, Guido Bibra, Ian Harris, Giselle Severin. Hello to all of you, and welcome to another special episode of Astronomy Cast.
And I will start looking at the camera in a moment. I was simply desperately attempting to share things out on CosmoQuest's Google Plus page and being very confused.
Share on all the places.
All of them.
All of them simultaneously.
I admit I only shared on Twitter and Google Plus. If anyone is a master of if this, then that, I really need a crash course. Like someone to very patiently crash course me.
There's me.
You're an if this, then that guru?
Yeah. And Zapier, which I like even better.
Okay.
Yeah, I run a pile of pretty cool advanced IFTTT recipes and Zapier recipes. But it's not magic, so it's not going to do what I think you want it to do. I know what you want it to do, and it's not going to do that. Which is, you want to be able to just have one place where you put things in and then it shares them out across all the places. So, yeah. No.
Doesn't? Okay.
No, there's two, because each one is just too specialized. Yeah, and you have to sort of you can have a really cruddy version of it shared into all the different places simultaneously, but if you want like a proper one that has like a nice picture or a link to the video or things like that, no, you got to do a lot of stuff manually.
I need a minion.
Minion, yeah. You know, I'm getting to a place though where I'm kind of like, you know what? I don't want to do all of that stuff anymore. Like, I don't think like Twitter, Facebook, it's all important, but at the same time, it's like time that gets taken away from making videos or writing articles or things like that. And I'm sort of getting to a place where I feel like I just want to shut it all off. I built a new phone and I shut off all of those services, right, on the new phone. And so it literally, all it has is my podcasts and email and Slack. And that's
yes.
It. And there's nothing else on the phone. And it runs fast and it doesn't bloop at me all the time. It doesn't tweet, it doesn't Facebook, it doesn't do any of that stuff. So anyway, but maybe I'm just, it could be, the fact that we have a lot of people who want to interact with us and that we need to interact with, we could have worse problems.
We could. That is entirely true.
Anyway, so we're going to do an episode of Astronomy Cast. You're going to watch it happen. And then we're going to stick around and answer some of your questions about space and or astronomy.
And I have people painting my house. So if you see weird shadows, I'm very sorry. We're trying to get it done before the snows start and stick, because it did snow over the weekend. And if you see a dog, it's because if the dog is anywhere else, she will bark at the painters. And it's that Monday.
Mm-hmm. I've got 2 dogs right over there ready to bark at a moment's notice. So it's just the life we live. Let's get our recording software going. Oh, I already have my recording software going.
I do not.
Okay.
And I'm not sure where my record button is.
That's unusual.
I upgraded GarageBand. Like, I actually have no clue. There it is. It's just, I think. No, I have a stop and I have a play. That is highly confusing.
That's pretty weird.
I'm going to close it and reopen it because that just has me confused. Sorry, Internet. I'm having the Mondays. Hello from Canada. I see from Brandon Musa. Hello from Illinois.
Hello from Canada. West Coast. The Hawaii of Canada.
That's a very strange way to put it. I still have no record button. Let's make this window bigger. Let's see if there's a different way to solve this problem. You'd think of all the buttons to hide, that wouldn't be one of them.
Ryan Schmidt says, I'm still using the old G+. Don't like the new one. Again, Ryan, life has changed. Get with the new program. Google won't let you use the old one forever.
I have a record button.
Oh, good. Good. All right, then. I'm going to press record when you're going to press record.
Okay. I pressed record. It's not. Yes, it is recording. Hi, Preston. I'm using GarageBand, the new version. It may do weird things. I'm sorry.
I have also pressed record. Astronomy Cast, episode 394, Bosons. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos. We'll help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. We just recorded a whole new batch of videos with some great topics. So if people haven't already, they should go and subscribe to the Guide to Space or the Universe Today channel over on YouTube. I'll let you figure out how to find it. Yeah. What's happening over there?
It goes. It is moving into the holiday season. It is when we're recording this the Monday before Thanksgiving, when you are probably getting this in the podcast feed. It is the Monday after US Thanksgiving, which is that Internet Shopping Monday. And so if you are one of those people that pay attention to this sort of insanity, and even if you're not, I'd encourage you, go check out astrogear.spreadshirt.com. We have CosmoQuest and Astronomy Cast and other random astronomy-based shirts, mugs, things like that. If you're watching live, I'm wearing my series, The Other Former Planet shirt, which is my team series shirt. So yeah, go get some astronomy stuff to inflict on everyone you love for this holiday season, whichever holiday it is that you may be choosing to celebrate or avoid.
Smooth product placement, Pamela.
I had to try.
All right. All fundamental particles are either fermions or bosons. Last week, we talked about quarks, which are fermions. This week, we'll talk about bosons, including the famous Higgs boson, recently confirmed by the Large Hadron Collider. Okay. So I barely understood last week, and I think this week is just going to really confuse me. But at least I think we can classify, as I mentioned, we can classify everything, either fermions or bosons. Fermions, quarks, I'm good. Everything else, bosons. What's a boson?
A boson is, by definition, a particle that has an integer spin. So they have a spin of 0, 1, 2, 10,000. That's still an integer. We haven't found any with that spin. But if we did, it would be a boson. So to recap from last week, we talked about fermions last week, which can add up to different things, but they all have spin. that's a multiple of 1/2. So 1/2, 3/2, 5/2. And fermions generally come in two species. There are the leptons, which are individual particles that we can encounter in real life. So there's things like electrons, muons, which are unstable, tau particles, which are unstable, but they exist. And then there's the refusing to interact with anything neutrinos. These are also leptons. So you have the electron neutrino, the tau neutrino, the muon neutrino. So those are all fermions. Those are all spin exactly 1/2.
Right.
Then we have the quarks. Now, the difference between the leptons is leptons are spin 1/2, and they have a charge of 0 or -1, and their antiparticles have a charge of +1. Quarks, to be weirdo freaks, have an electric charge of either 2/3 or -1/3. And if it's the antiparticle, just flip that inside out. So, yeah,
Right.
weirdo charge.
Right. The charge makes almost sense to me just because, we've done enough chemistry and knowing how charges of particles come together and turn into atoms. And it makes sense that if you add 2/3 and you minus 1/3 and minus another 1/3, then you have a neutral charge. And if you add 2/3 and then add more thirds, then you get a positive charge. So I think that all makes sense. But when you talk about spin, what does that mean?
It's just an adjective that we applied to some weird quantum thing. And the reason it matters is if spin is 1/2, and it's not actually spinning, it's just a word someone came up with. It's not actually spinning. But if it has a spin, useless adjective used for historical reasons, if it has a spin 1/2, then the Pauli exclusion principle applies. And these are things that insist that nothing like them can share an energy level. So these are your Diva particles. If you have an energy level in an atom, that energy level can only have one spin up, and then it can also have one spin down, because those are two different things. And the Pauli exclusion principle says you can only have one of each of these things.
So it is not that the particle itself is spinning at any rate.
No.
It is,
it's just an adjective. Just go with it.
Okay. All right. But the point being that and the Pauli exclusion principle is really important because that's what stops necessarily them. You can't have two particles that have the same spin in the same spot, right?
Exactly.
Yeah.
Exactly. So bosons have a spin of 0, 1, 2. In all practical uses that we find them, they have spins of 0, -1, or +1. So these integer spins, they don't have any of those Diva-like characteristics to them. In fact, in Bose-Einstein condensates, if you lower the temperature of a conglomerate of bosons enough, all the bosons are going to try and plow themselves into a single energy level. And this is where you get really weird physics going on.
And so they're almost doing the opposite of the Pauli exclusion principle. They're trying to get themselves all into this aligned state, right?
Exactly. It's like, can I be the lowest energy level? Why, yes, we can all be the lowest energy level.
Let's all do it together.
Exactly.
Right. And we actually did a whole show on Bose-Einstein condensates, which are this strange situation that these bosons get into. But okay, so we've talked a bit about some of its fundamental kind of characteristics about its spin, but why are these things important? Why are these, where do we find them? What do they how do they make up, we talk about all the different particles and how there's the nucleons and the protons. So where do the bosons come in?
So the bosons come in by literally saying, we are going to organize all of you, and they tell everything what to do by being the force carriers.
Force carriers. Okay.
Yes.
Okay. And so what kinds of forces are we talking about?
All the forces. They're non-discriminatory, although they do form unions. So you have all of the photons are like, and we shall be the ones who mediate the electromagnetic force. And if you have two things that are repelling each other because they have opposite charge, because they have the same charge, or attracting each other because they have opposite charges, or you have things that are magnetically attracting or repulsing each other, that's all because there's photons in there mediating that force, communicating the force between the two things that are either attracting one another or repelling one another.
Okay. So, I mean, what about the strong nuclear force and the weak nuclear force? Is that bosons mediating that as well?
It is bosons all the way down. So with the strong force, here you're starting to look at what are called gluons. And we generally just kind of lump them all together and say gluons, but in reality, there's 8 different gluons. And this is because, again, don't get excited. We just used a word. It has no real good meaning. We refer to the quarks as having colors.
Oh, no.
So to make things worse, we like go through and start calling them things like blue and red and stuff like that. Just go with it. Just go with it. And so these 8 different types of gluons are there gluing the quarks together. And
right. And so I think the thing with gravity, of course, is they've been searching for the boson version of gravity.
Right. And that
graviton.
Exactly. Now, where things get different between these different things is so our photon, it actually has 0 mass, which is why it can get the speed of light. That's very exciting. And the photons conveniently have absolutely no charge. Otherwise, our universe would be kind of a mess because moving charge creates magnetic and electric fields. And just imagine if all the photons were creating fields, that would be really bad. So luckily, photons are out there with 0 mass, 0 charge, conducting the electromagnetic force. Photons are the reason your refrigerator magnets stick to your refrigerator.
So a photon is a boson that we are familiar with.
Yes. Then we also have the gluons, which are conducting, mediating, if you will, the strong force. They're the ones that are gluing the different kinds of quarks together. And we also refer to the way the protons stick together inside of the atom as residual color force. And so the gluons are actually just holding that whole nucleus together with that residual color force.
So I wonder how that kind of works when I think about like photons. You know, when something generates a photon, the photon moves across space, strikes my eye, you know, creates an electric current in my brain. That is the force being mediated across that distance.
Not quite. So this is where it gets really confusing. So
good. I'm glad it starts getting confusing now. Let it begin.
So I have to admit, what I tweeted in preparation for this show was, "Oh dear God, particle physics hurts." So we experience photons on a regular basis because they're generated by lots of different things. They're being generated by chemical reactions in glow sticks. They're being generated when you add electricity to gases and it excites certain photons. All sorts of different processes generate photons, including some nuclear decay processes. And these free-range photons that may eventually end up hitting our eye in a meaningful way that leads to us perceiving something, these free-range photons aren't necessarily the ones that are carrying around force. What it turns out is that refrigerator magnet that you have stuck to your refrigerator, there are what are called virtual photons going back and forth between the refrigerator and the magnet, carrying all of that force around with them. And we don't actually get to see those as light, just to be confusing.
Great. No, that makes complete sense. But they, I mean, I guess these virtual photons, they move at the speed of light, which is
Yes.
sort of magnetism moves at the speed of light. So,
Yes.
Okay, great. So then how does a particle accelerator, you know, like the Large Hadron Collider, pull some of these particles apart, so you can actually say, there is one of these, one of these bosons.
So what's interesting is in the colliders, it's not pulling things apart in order to reveal these things. What it's actually doing is it's revealing them by creating a large blob of energy, actually a very small blob of energy, and that energy condenses out into mass. So when you take a particle accelerator, and quite often you will accelerate two different particles in opposite directions and smash them into each other, or smash a stream of particles into a stationary target. You're smashing things together in either case. And in the smash, you're taking all of the kinetic energy that the accelerator has given to that particle. So we've translated electricity into creating electromagnets. Those electromagnets have then done work. They've moved and accelerated those particles that are being accelerated, whether they be positrons, electrons, protons, whatever. And then all of that kinetic energy plus the mass, so E equals mc squared, gets smashed into a small region, and all of that energy gets liberated and then has the chance to recombine into whatever it is that enough energy was confined to produce. So
right, however the math holds out. Like if I dumped a pile of Lego pieces in front of you and said, build whatever you can with these pieces.
Exactly.
Right. That is the collision of those particles. They smashed all of the energy put into them. You get an amount of mass equal to that total energy. And then however, let's build a Higgs boson. We got a little left over. Let's build a couple of photons and maybe a neutron.
Right.
That's what we've got. And then they'll decay. Right.
So with the gluon, for instance, and I'm looking these numbers up so I don't screw it up. So a gluon itself has a mass that is actually zero. It is a mass zero particle, but it does have this energy, and that energy, we're able to see how it interacts with stuff. So it's not like we are actually detecting gluons directly. We're seeing how it all fits together, how they're delaying and expanding different reactions. Now, we luckily can start to directly detect, or at least via their decay particles, the next kind of boson, which we haven't discussed yet, which is the W and the Z bosons.
Then let us begin.
So what force are we missing?
Hold on. We talked about the strong nuclear force. So is the weak nuclear force?
It is the weak nuclear force. So the weak nuclear force is the force that allows quarks to change identities. So, for instance, we know experimentally that a neutron left alone on a shelf is not going to stay a neutron. It is going to decay into other things. It's going to decay. The proton that gets left over is what we notice the most, but as well as the proton, we have an electron go flying off, and we have an antineutrino flying off. And this is because the electroweak force allows, via the W bosons, an up-type quark to exchange with a down-type quark.
Okay.
Still with me?
Mm-hmm, mm-hmm, yep.
Okay. So these W bosons, which do this awesome thing we need, they are able to decay into things that we can track in accelerators. So for instance, we've seen positrons and electron neutrinos. This is an up quark and an anti-down quark are another type of reaction that goes into this. And then we also have a charm quark and an anti-down quark, if I'm reading these equations correctly, is another way that these can also be spotted. So you have these different combinations. There's another combination that is a muon and a muon neutrino, or you could have an up and a strange quark or anti-strange quark. There's all of these different combinations, but they add up in specific ways where we can balance out all of the qualities, all of those color qualities, all of those spin qualities, all of these different things. And we know, hey, all of these things add up to the same kind of critter we're not directly detecting. And that critter we've named the W boson.
And the Higgs boson is sort of follows from this, right?
Sort of. So
I mean, I know the W and the Z boson were only discovered, I mean, fairly recently.
Yeah,
I mean,
they were discovered in the 80s.
In the 80s, yeah.
Yeah.
And so, these were some of the last pieces to come together to really hold together the standard model, except for the Higgs boson.
And what's cool is the Z boson actually gets its name from having zero electric charge, so Z is for zero, and because Steven Weinberg said it was the last particle needed for the standard model. And
the W's are for the weak force.
The W's are for the weak force,
yeah, and the Z is for zero. Yeah.
And the W's, the reason we're saying plural is because there's one with a negative electric charge and one with a positive electric charge. And this is really just the particle and antiparticle. But we see them both. We refer to them as the W minus and W plus. I don't know why. That's just what we do. Sort of like we have electrons and positrons.
I wonder if like a particle physicist wants to just go and just restructure the whole thing just to make it a lot more straightforward, to, make quarks have charge 1 or, negative 1. To come up with new terms instead of spin and not give them colors, to really like the periodic table of elements, like when that was put together, it, really made a lot more sense. And I think someone needs to come back around and take a crack at redoing particle physics entirely. So if anyone wants this job, I got a Nobel Prize for you.
Well, no, you're just asking people to rename things.
I guess so.
So now you sound like the French Council on Words. No, it's
Mais oui.
Yeah. It's really just a matter of in struggling to try and make it linguistically possible to talk about all of these complex particles and all of their various attributes. People grabbed at words that describe normal three-dimensional objects, and normal three-dimensional objects spin. So let's say that electrons have spin up and spin down, and normal everyday objects have color. So let's just call the quarks weird thing that they do color force, or color charge. And the theories we have all work perfectly well. There's just linguistic weirdnesses to them. And a lot of the linguistic weirdnesses are just historical leftover echoes. The electron and positron turned out to be a particle-antiparticle group. And we just ended up with the two names instead of saying the anti-electron.
Right.
It's history.
Yeah, but won't Weinberg feel embarrassed if they find other particles after the Z particle, right?
And he was one of the ones that was involved in supersymmetry. So if supersymmetry becomes true, which is next week,
right.
then he will be the one to blame for all of the excess stupidly named particles that are in our future. Because
there's like a whole, supersymmetry, as per the name, is a whole set of particles matching all the particles that we know about way off into supersymmetry. And so you're going to need to invent whole new letters.
It's like going from normal chess to three-dimensional chess.
Right. So I mentioned briefly, where does the Higgs fit into this, the rest of these bosons?
So this is where we start getting into additional strange words. So when we talk about the W and Z bosons, we often call them intermediate vector bosons. I don't know who gave them this word. Again, more adjectives. But what comes out of them being these intermediate vector bosons is they have mass. Then we have the gluon, which does not have mass. and it's also called a gauge boson. So you have this massless, chargeless thing versus this has mass, either does or doesn't have charge thing. And then with the Higgs boson, you now have a scalar boson. So we have a scalar boson, a gauge boson, and an intermediate vecton boson family. The Higgs is the scalar, and the Higgs is hanging out there with a whole lot of mass and no charge whatsoever, which is, again, good because gravity is kind of everywhere. The Higgs boson was needed to figure out how the heck things ended up having mass. And the explanation is that the Higgs bosons, just like your photons are going back and forth on the refrigerator, holding the refrigerator magnet to the refrigerator, the Higgs bosons are going around, not coupling things to the Earth, not coupling anything to anything, really. But what they're doing is they're coupling everything to this background scalar field, the Higgs field. And it's in this coupling that the Higgs bosons are responsible for things having mass, responsible for things having the characteristics of inertia and momentum. And the more strongly things couple with the boson, the more with the Higgs boson, the more Higgs bosons are partnered up with something, the more mass it has, the more inertia it has, the more momentum it has as a function of how fast it's going.
And so when you have a lot of mass, then you have a lot of Higgs bosons.
Yes. You are well loved by the Higgs bosons. Yes.
Right. And when you're moving quickly, you are
still just as coupled to those Higgs bosons.
But making them angry?
Well, no, the Higgs bosons really don't care. All they care about is thou shalt have momentum and inertia and giving that to you. The way to think about it is, and this is not my own analogy, this is one that I read many, many years ago, and I wish I remember what magazine it was in. I want to say it was Scientific American, but I could be wrong. The initial analogy I read is it's like a rock star with a posse. As they try and move through the room, the bigger the posse, the more people are going to turn and look at them, and the harder it is going to be for them to move in general because they have to move this whole posse with them. If you have someone who's not famous and has no posse, they just move through the room, there's nothing slowing their ability to get going.
Right. Low mass.
Low inertia as well.
Yeah.
And so the bigger your posse, the more Higgs bosons you have attached to you, the harder it is for you to get moving. Now, once you're moving, you're cool. It's that whole an object in motion stays in motion, an object at rest stays at rest thing. It's the getting from the moving to the not moving, or from the not moving to the moving, where the Higgs boson really matters.
Right. Okay. And so are there any sort of bosons, apart from going into the supersymmetry, are there any, and I guess the graviton, right, is the missing boson at this point?
Yeah. It's kind of the one that doesn't even end up on the chart, except occasionally as like an asterisk. If the graviton does exist, and we don't know if it does, and that's kind of messy to think about. If the graviton does exist, it doesn't have mass, doesn't have charge, it doesn't have spin. Well, it could have a spin 1, but it doesn't have charge and it doesn't have mass, and it's out there communicating gravity the way the photon is communicating the electromagnetic force, where it travels over vast distances and it's flying around everywhere. But we don't know how to detect it. We don't know if it's required. It doesn't necessarily seem to be required. And this makes people highly uncomfortable. And this is where you start having to think perhaps too hard. And this is one of those 4 a.m. semi-drunk conversations that people get into,
right?
Where Einstein often encouraged people to think of gravity as the shape of space, where gravity actually distorts space. But that's not a particle physics phenomena. So are we looking at two totally different paradigms or not? And this is where it's best just not to think about it too hard unless you're a theorist chasing down that Nobel Prize, in which case don't have more than two collaborators.
Right. And anyone who does turn up the gravitron Nobel Prize.
Exactly. Again, only work in collaborations of three.
Of three.
Or fewer.
Yeah, and most of the papers coming out of the Large Hadron Collider are in the hundreds of collaborators.
Right.
So it's going to be tough. All right, so let's see if I have this wrapped around my head. Are you ready?
No, but go ahead.
Okay. So the bosons are the particles that mediate the various fundamental forces.
Yes.
And so the one that we're most familiar with, the one that's associated with electromagnetism, is the photon.
Yes.
There are also, with the strong nuclear force, we've got the gluons.
Yes.
And with the weak nuclear force, we've got the W and the Z, or you may pronounce it Z, bosons. These are the ones that mediate the weak nuclear force. There is no boson yet for gravity, which, if it could, would allow us to finally merge all of the forces together into one beautiful put the universe on a t-shirt theory, but that doesn't exist. That would be the graviton. Yes. And the Higgs boson is the fundamental force that mediates mass, as we understand it.
Yes, it's not really a force. Well, other than you tried to call mass a force, which...
Right.
Other than that, you did great.
It's the particle that mediates mass.
Yes. Yes.
Okay. All right. So there you go, everybody. So now, and just to summarize from last week, right? The leptons, they are the fundamental particles that create
stuff and
protons,
things.
neutrons, things like that, as well as the neutrinos and all of their antimatter equivalents. And we've got the bosons that create all of the particles that mediate the fundamental forces in the universe. So next week, what's left? We said all of the things on the one hand and all the things on the other hand. So what's left?
What's left is why we still have the Large Hadron Collider and the Fermi Accelerator being added to and built upon. And this is trying to figure out what the heck is dark matter and how do we explain dark energy and what are the theories beyond the standard model that people are grasping at with these instrumentation packages.
Is it possible that we only understand half? And that now with supersymmetry, there's a whole nother half to figure out.
It's way bigger than half. It's way bigger than half. It hurts.
Okay. All right. Well, then I think I look forward to things getting even more complicated next week.
Excellent.
Thanks, Pamela.
Thank you.
All right. Save that.
Yes.
What did I say this was? 394?
Yep.
Wow. Episodes. All right.
Okay. That worked.
Okay. Questions for question time. We're going to say hello to Lauren Dankowicz. Hello, Lauren. Nancy said that. So, whoa. So Nancy says, woohoo, Meat Instruments has been running a contest on Facebook. Their 10-day grateful giveaway. I just notified that I am their day 8 winner. Just won a pair of 10x50 travel view binoculars, classic photo tripod,
awesome.
and a tripod adapter for the binoculars. Yeah.
Yes.
That's terrific.
That is awesome.
David Fairweather says, hello from New Brunswick. We got a bunch of Canadians. This is awesome.
Yeah. Go Canada.
Guido Bieber says, well, if Fraser says he barely understood last week's episode, then I think I can safely say that I'm very glad I don't have to take a test or an exam about this. You do, Guido. This is a nightmare that you're having, and the test begins now. Stephen Walker says, let's hope for good internet bandwidth this week. It was. Your bandwidth was great.
I think we did okay. Yeah. Well, Kyle actually went and rebooted all the routers in the house right before we recorded, which actually caused a moment of complete panic, but it seems to have paid off.
David Joseph Wesley says, I will have tons of new Higgs boson buddies post-Thanksgiving dinner this week. Yes.
That's true.
That is the downside of Thanksgiving.
We have Giselle from sunny but cool Quebec.
Yeah. Jim Meeker says bosons are force carriers, so they're like midi chlorines. I was actually trying to think about how I was going to sneak a force joke into that as we were going. I had one queued up in my brain, and then you distracted me, and I couldn't unleash the joke. So, let's see.
Lonnie H over on Twitter writes, "Great cast today, y'all. My brain hurts, but in a mostly good way, I think."
Oh, good. Michael Job says, attracting force is love and repulsive is hate. Michael Job also says, boson the clown. That sounds about right. David Fairweather says, I bet a lot of particle physicists would not like to learn new terms. It's not about them. It's about us. It's about us. Okay. I think I'm gonna take it on myself then. I'm just gonna sit down and I'm gonna just rewrite the names.
You're gonna change all the Wikipedia entries.
Well, I will propose new changes to the Wikipedia entries after I've changed all the names. But I have to come up with like a better analogy. So I'll work on that, and then I'll write a book. Hey, we're only like 3.5 weeks away from The Force Awakens on the 18th of December.
I know.
Isn't that crazy?
Yeah.
And Mike Vogel says, if light waves redshift due to the expansion of space-time in relation to the expansion of the universe, do they also change the wavelengths due to gravitational waves? Could you see the effects of gravitational waves on light waves when they travel the same way? Yes. Is that right?
Well,
so if an object is generating gravitational waves, which have never been directly detected, but that object is moving away from us very quickly, those gravitational waves are going to redshift?
So the gravitational waves are moving at the same speed as the light. So what ends up happening is we get the light and the gravity wave actually distort everything. So it sort of becomes, what direction are you looking in? Because that's going to depend on how things get bent. So for instance, what LIGO's...
Well, the same as light, right? So if a black hole is moving quickly away from us and it's generating, and let's say it's a quasar and it's generating light, and that light is redshifted because it's moving away from us, and it's also, say it's orbiting, it's actually two black holes orbiting each other, and that's generating gravitational waves, and they're moving away from us. Are those gravitational waves going to be redshifted because the source is moving away from us?
The gravitational waves will compress us when they get to us.
Yes, but will they compress us differently as if that black hole pair was moving towards us as it was generating those gravitational waves?
I don't think it works that way. No, you suddenly wandered into a domain register where the answer was not that straightforward. So in the framework of the observer, if your reality gets squished, that squished reality, the wavelengths in it are going to be perceived differently. It gets really confusing quickly.
Right. But I guess the question is there any difference from the gravitational waves coming off, a binary pair of black holes that are racing towards us?
Let's actually bring this back into reality. So if we bring this back into reality and get rid of gravitational waves, which are their own specific thing, and say instead, does the effect of gravity deter the light? Yes, you get gravitational redshifting off of objects where something with a very strong gravitational pull will actually hold back the light, sort of, kind of, is a way to think of it. Removes energy from it, and you end up with gravitational redshifting.
But imagine if there's no such thing as light and there was only gravity.
It would be really boring.
I know. I'm just saying, trying to break this apart. Okay, let's move on. And the phone is ringing, and I'm gonna ignore it. Thomas Reiner asks, what is a must in your opinion of a space expo?
Okay. That gets tricky because some space expos are all about unmanned space, some are all about manned space, and some of them are all about let's go in our backyard and look up. If it's a let's go outside and look up space expo, then a must for me is that booth that is all about the astrophotography. So like the World at Night folks sometimes do booths like this. That's Babak Tavarish. Then having that like amazing, let's look at all the eyepieces. Teleview eyepieces have been known to like suck me into just kind of becoming a junkie standing there high on optics. Then that ability to compare all of the different types of telescope mounts, all of the different types of telescopes, that giant vendor room where you can actually figure out what do all of these words that you hear about on Astronomy Cast, what do they actually look like when you have that Schmidt-Cassegrain telescope in front of you as compared to that achromatic refracting telescope. So to me, my favorite space expos are these amateur astronomy ones like the Northeast Astronomy Forum, NEAF that occurs every year outside of New York City, where you can walk around and see all the amazing things that are being done by astrophotographers and observers. So that's the science as well as the pretty pictures. And then you can look around and look at all of the equipment that gets used to do it.
David Joseph Wesley asks, any good books or other sources to get a better grasp of this mind-bending topic?
What I would actually do is start by watching the movie Particle Fever, because that gives just like a really neat insight into how colliders work, the search for the Higgs boson. It's just a kind of cool movie, and it also gives you way too much insight on how narcissistic particle physicists can be and how much they're chasing science instead of anything else in other cases. So it just, all these different personalities that you don't normally encounter when you're out at the library. You find all of these amazing different personalities in particle physics.
It was interesting to talk to particle physicists about the movie.
Yeah.
Because they, you know, I mean, like anything, right? Like for me as a person that knows quite a lot about physics, I was entertained by watching the movie. And it's on Netflix, I think, if you want to watch it there. But for the people inside of it, they were like, well, you know, they missed a bunch of stuff. And they actually, you know, they raised the level of you know, conflict, and they put events in different orders to make it look cooler because it didn't really go like that. It was quite funny.
In terms of like a good review book on particle physics, I'm not coming up with one right off the top of my head. I'd actually have to go stare at my bookshelf in my office on campus where the internet is quite bad, which is why I'm not there right now.
What about Brian Greene's one?
No.
Because I mean, I know
that's string theory.
No, I understand that. I know he's a string theorist, and I know that's where
it's a beautifully well-written book about stuff that may not exist.
But doesn't he give a good job of setting the groundwork for the first few chapters to get you to the place where he then goes off into string theory land? Right? That's all.
The problem is, so the problem that I have with that book is it has turned so many people into acolytes rather than into scientists. And I struggle recommending books where people walk up to me later and say, this book is my Bible, and it's not thoroughly based in testable science.
So I guess anyone who's watching this can provide some recommendations.
Yeah.
That would be great. It is a tough one though. I mean, Feynman did some great work in sort of helping to describe them when he wasn't being a total creep. But so, you know, surely you're joking, Mr. Feynman, and you know, you're going to get sort of little bits and pieces of it. But I've actually got a book that I haven't even cracked yet. It's called The Neutrino Hunters. that I'm
Yeah,
gonna.
that was actually really, really good.
Yeah, I'm gonna read that. But no, I can't think of a great that just jumps off.
See,
The
I
way
read
there's like stuff with black holes, like you can read Hawking's A Brief History of Time and get a really great understanding of his thoughts on black holes. But
there's some really good books out there. I'm just completely failing to remember what they're called, which isn't particularly useful. I can see exactly where they are on my shelf. Again, not really useful.
Yeah, I would love to know sort of if the people watching this have some good
When
opinions.
I'm on campus next, I'll tweet things out.
Yeah. Let's see what else we got. Anything? Ed Thompson asks, do you have a recommendation for a digital camera for taking pictures through a telescope? I currently own a ZWO Color, but I was wondering if there might be a better option you might think might be better.
So it all depends on how much money you're looking to spend. If you're looking to have a dedicated astrophotography system, I would get whatever S-Big color anti-blooming camera for astrophotography, not for science. Don't get anti-blooming for science.
Yeah.
Whatever the coolest, most awesome S-Big you can afford is. If you're looking for a dual purpose unit, something that can be used both for astrophotography and for everyday photography, I go with Canons. Get whatever the most expensive Canon you can afford is. For me, that's the T series. I think that Fraser has the same series camera. His is just more modern than mine.
I've got a 5D.
Yeah. Okay. So you've
a full frame.
Jumped up. Yeah.
Yeah.
So.
But I mean, the great thing about that, right, is, the mount for your camera onto your telescope is fairly inexpensive. And then you can use that camera for all kinds of stuff and bolt it onto your telescope and take really great astrophotography. But as you mentioned, I think that for the first group you're talking about, those are the black and white ones, right?
No, they actually have color CCDs. It's a combination of 3 sets of pixels now.
Right.
Don't use those for science either. So if it's color and if it's anti-blooming, either of those two things, not for science. If you want to do science, you want yes, it will bloom on you, and you want a black and white, which is just light or no light and a filter wheel.
Yeah. Yeah. So if you only want to take pictures of connected to your camera, even something that's going to be dedicated, you're going to bolt it right onto your telescope, then go that way. And if you want something that you can use for other purposes, I mean, you can pick up an old Canon EOS off of Craigslist and stuff for like $100. And
some of them have had their infrared blocking filters removed. And if you do that, you have something that's particularly good for astrophotography. Now, the highest resolution, best quality astrophotography is always going to come from using a black and white CCD, Finger Lakes, S-Big. Those are the 2 big commercial producers of CCDs, and then get a filter wheel where you combine broadband filters and emission line filters. So emission lines are like your H-alpha filter that zeroes in on the light coming from hydrogen and nebulas. It's your sulfur filters, which gets you those amazing oranges, and oxygen filters. So these narrow line filters pop different features in nebulae, and then the broadband filters, they allow you to build up that general color picture.
There you go. Let's see. Richard Drum says, a little off topic, if space is expanding and space-time is a thing, is time also expanding?
No.
No. Okay.
Because time is defined by the speed of light, which is a constant.
Boom. Hugo Burnham asks, if the Higgs field exists, is it a part of space-time?
That's a question for philosophers.
Pete Drummel asks, wow, everyone's talking about things expanding. If the universe and the fabric of space-time is expanding, does that include the space in between the atoms themselves? What about the relative size of the particles themselves? No, they are not. Space is expanding. The particles themselves and the space in between, even
those
the size
are held
of the
together by other forces.
Right. Gravity, strong electric force.
Yeah.
Yeah, strong nuclear force, weak nuclear force, etc. So,
and explain this to children, because I grew up in a weird family. I was told about the expansion of the universe when I was little, and I like went to bed terrified that like at some point in my life things would expand to the point that my neurons could no longer talk to each other. So like you can accidentally terrify a small child. So explain that we're held together with the electrochemical force or electromagnetism through chemical reactions. And so we're only expanding by eating too much, not because of the expansion of the universe.
Right. Okay, got a few recommendations. So Pete Brummel says Chad Orzel has 2 good books. John N.K. Vogel says Companion to the Cosmos by John Gribben.
Yes. Yes, that's the one I couldn't remember the name of. Yes.
Okay. Pete Brummel also suggests John Butterworth's Smashing Physics, Frank Close, Neutrino. What else here? I think that's it.
I actually really like pretty much all of John Gribben's books.
I haven't read any of his books.
Yeah, he's a really good science writer.
Wow.
So yeah. Pretty much I strongly recommend anything he's written. Him and Timothy Ferris are kind of like 2 of my favorite science writers.
Timothy Ferris is great for astronomy stuff. And then, not the 4-hour workweek guy. No. Although apparently they live very close to each other and are aware of each other's presence. So it's very funny. Okay, well, let's wrap this up. Pamela, thank you so much.
It's been my pleasure. And I will see you post American Thanksgiving feasting, which in my house I think means a day of just playing with the dogs.
Okay.
So
is that going to be on Friday?
Thursday.
Okay.
So don't forget astrogear.spreadshirt.com. Get your series Former Planet Also shirt.
Awesome. All right. Thanks, everyone. Thanks, Pamela.
Bye-bye.